Alright, so in today's video we're going to be continuing with limits, and we're going to be finding limits using a table. Okay, so let's really just get into it and try and find the limit of some function here. So the question is, if we have some function and that function is going to be x minus 1 divided by x squared minus 1, the question is, what is the limit? So what is the limit of this function as x approaches 1? So that's the question. So first thing we should do is we should write this as a proper limit. So this is the, remember, limit as x approaches 1 of the function f of x. In this case it's x minus 1 divided by x squared minus 1. And what is that limit equal to? So that is going to equal something. We don't exactly know what yet. So we can put a question mark there. That's the question. And now we ask ourselves, okay, how are we going to answer this? Well, there's a very basic kind of method to answering these questions, really with any limit, and that is by using a table. So, and what I mean by a table is we're going to have some sort of x values, and those x values are going to be centered around this number 1 because we are approaching 1. And ideally what we want is we want to approach 1 from the left-hand side and from the right-hand side. So in our table, we're going to have numbers that are a little bit less than 1, and on the other side of the table we're going to have numbers that are a little bit more than 1, but both sides are going to be getting closer and closer to 1, and we're going to see what happens to our resulting answer, or to f of x, when those numbers get closer and closer to 1. So the way we can arrange this table is we can have our x values up here and our f of x values down here. Okay? And now all we have to do is choose some sort of x values. Sorry, let's make this a straight line. Now all we have to do is choose some sort of x values. Okay, so in the middle here, we are going to have the x value of 1, because again, we are approaching 1. So that's going to be right in the middle, and we don't really care what happens exactly at 1, we just care what happens as we get really close to 1 from the left-hand side and the right-hand side. Okay, so at 1, we don't really care what the value of f of x is at 1. And in this case, we actually can't even get a value for that, because if we substitute 1 into here, we're going to get 1 squared minus 1. 1 minus 1 is 0. We know we can't have 0 in the denominator. So even if we wanted to get a value at 1, we can't. But what we can do is we can get values really close to 1. So for example, maybe we want a value at 0.5. Okay? So when x is equal to 0.5, what is f of x equal to? Well, if we plug that into our calculator, you'll see that we get 0.66 continuous. Okay, or 0.67, doesn't really matter, 0.66. Okay, so that's kind of a nice starting initial value. Let's get even closer to 1 now. Maybe I want to do 0.9. Okay, that's even closer to 1. So what happens if I do 0.9? What do I get for f of x? Well, again, if I type in 0.9 here and put that into my calculator, I'm going to get 0.526. And there's some more numbers there, but let's go to 3 decimals. Well, okay, so logically the next question should be, well, what if I do something like 0.9999999? And you can add more 9s if you want, or you can do 1 less 9, doesn't really matter, but the point is that this number is really close to 1. It's not quite 1, but it's extremely close to it. And so we ask ourselves, well, what do we get here? And well, we see that we're going to get 0.5000. Okay, and again, we can only go to 3 decimals if we want. We'll go to 4 here, but the point is that we get 0.5000, and there's probably some other numbers later on there down the line, but we're getting close to 0.5 here. Okay, and now let's take a look from the right hand side and see what happens. Well, I like to keep things symmetrical, so on the right hand side, let's start with, instead of 0.5, let's start with 1.5. Okay, so 1.5. And we ask ourselves the same question. What happens if we go with 1.5? What value do we get? Well, we get 0.4 on the dot. Okay, well, let's get even closer. Let's go with 1.1. And what do we get here? Well, we're going to get 0.476. And then again, we can ask ourselves, well, what if we get even closer? What if we do 1.0000001? And what we'll see is that we're going to get something along the lines of 0.4999. And again, there's some other decimals here, but the idea is that as we get closer and closer to 1, we're getting closer and closer to some sort of a number, ideally. Okay? And we can ask ourselves, what happens as we approach 1 from the left-hand side, or from, numbers smaller than 1? And what happens when we approach 1 from the right-hand side, or numbers bigger than 1? And the way that we can indicate that, actually, is here we are letting x approach the number 1 from the left-hand side. And the way we're going to indicate that is by putting a little minus sign kind of where the exponent would go. Okay? And on the right-hand side here, we're letting x approach 1 from the right-hand side, or from the larger numbers of 1, and so we put a little plus sign. And right here in the middle, if we really wanted to, we could say this is exactly when x approaches 1. So this is when x approaches 1 from both the left-hand side and the right-hand side, we can say. Okay? And so this kind of idea actually brings up an interesting conversation where we can have a left-sided limit and a right-sided limit. Okay, and there's actually an interesting rule that comes from that. So let's go over that rule. The rule is if the limit as x approaches, now I'm gonna generalize this and I'm gonna say some number a from the left of a function f of x. Okay, so if the limit as x approaches a from the left-hand side of f of x equals some number, call that number L, and the limit as x approaches a from now the right-hand side of that same function, f of x, equals the same number L, okay, so they need to equal the same number, then the limit as x approaches a just in general of f of x equals L. Okay? So basically what this is saying in English is if the limit from the left-hand side approaches some number, and the limit from the right-hand side approaches that same number, then the limit itself is that number. The answer is, well, it's that number. Okay, and so we look at our example up here, and we look at the limit from the left-hand side. So that would be this side right here. Okay, we can write this as the limit as x approaches 1 from the left-hand side. That number approaches 0.5, right? If we look at the right-hand side, we notice that that number also approaches 0.5. And so what we can say is, since the limit from the left-hand side and the limit from the right-hand side approach the same number, in this case 0.5, then the limit itself also exists and it approaches that same number. And so using that, we can say, therefore, the limit as x approaches a, just in general, of the function f of x, now in this case our function is x minus 1 over x squared minus 1, is equal to 0.5. Or I like writing it as a fraction, so I'm going to write it as 1/2, but either or works. Okay, and so we've answered our question. Our question is, what is the limit as x approaches 1 of this function, x minus 1 over x squared minus 1? And the answer is, well, it's 1/2. That is our final answer. Okay, and sorry, this shouldn't be an a. This should actually be, this should be a 1, because we're approaching 1. Okay, so there, we were able to answer a limit question using a table. Now, this rule here that I mentioned is kind of important, and it should raise the question in your mind of, well, what happens if, or is it possible that the limit from the left and the limit from the right don't equal the same number, don't both equal L? Maybe one equals L and one equals K, right? Two different numbers. L is one number, K is another number. Is that possible? Is that something that we can encounter? And the answer is yes, it is something that we can encounter, and I'll show you an example here really quickly of that. So let's just say we have some sort of function. Okay, here's our graph, and it looks like this is our graph paper, and it looks like this. Okay, this is just a random function. I don't know what this, this function's equation is, but it is possible to get functions like this. Okay, and let's say that here this is an x value of 3, this is a value of 1, and this is a value of -1. Okay, and this is our function f of x. Okay, so what we can do here is we can take the limit as x approaches. Now remember, we can take the limit as x approaches like this point or this point, right? But these points aren't interesting to us. We want the interesting points, and the interesting point is at x equals 3, right? So the limit as x approaches 3 of this function, again, I don't know what the function is, it's just some f of x, and we're going to approach 3 from the left-hand side, and we're also going to take the limit as x approaches 3 from the right-hand side of this function f of x. And we're going to ask ourselves, what are these functions equal to? So, okay, let's do the math. So, as our x value gets closer and closer to 3, what is happening to our y value, right? Now, we don't have an equation to plug numbers into and make a table like we did in the previous example, but we do have a graph that we can visually look at. And so what we can see here is as our x value gets closer and closer and closer and closer to 3, our y value gets closer and closer and closer and closer and closer to 1 as we approach it from the right-hand side. As we approach it from the left-hand side, as we go closer and closer and closer and closer to 3, our function gets closer and closer and closer and closer to -1. And so what we can say here is the limit as x approaches 3 from the left-hand side of this function f of x, so remember that's this side going this way, gets closer and closer to -1. And the limit as we approach from the right-hand side, so that's going this way, our function gets closer and closer and closer to +1. And so what we've just shown here is that it is possible to have a limit from the left-hand side and a limit from the right-hand side equal two different numbers. Okay, and these two limits do exist. Visually, we see they exist. The limit as x approaches 3 from the left is -1, and the limit as x approaches 3 from the right is +1. So these limits by themselves exist. But if we ask ourselves the general question, what is the limit as x approaches 3, just 3, okay? What is that limit? Well, that limit of f of x, that limit just doesn't exist, right? Because again, from the left and from the right, we get two different numbers. And if we get two different numbers, then the general limit does not exist. But its individual limits can exist. Okay, so there's an example of when the limit from the left and from the right do not equal each other, and therefore the general limit itself, also, because of that, does not exist. Okay, let's go over one more example here. Let's say that I want to find, let's say I have f of x is equal to 1 over x, and I want to find the limit as x approaches. Now, what would be an interesting number here? An interesting number would be 0. I think you would agree with me because, again, remember, we can't have 0 in the denominator. And so that seems like it would be a pretty interesting number to find a limit for, right? So again, let's write this as a limit. So this is the limit as x approaches 0 of 1 over x. And that's equal to, well, at the moment, we're unsure. Okay? And again, we're just going to create a table, and we're going to try and answer it. So let's create our x's here, and our f of x is here. Okay? And we'll draw a nice little line there, a nice little line here, and in the middle, we're going to have the number 0. okay? And again, we don't really care what happens at 0, and yet again, even if we did care what happens at 0, we can't actually figure out what number we're going to get exactly for 0 because we're going to have 1 over 0 and that's not allowed. But we can take numbers from the left and from the right of 0. So from the left-hand side, let's start with something like negative 0.5, and then maybe we'll work our way up to, let's say, negative 0.01, and then maybe negative 0.001. And we'll do the same thing on the right-hand side, right? So we'll start with positive 0.5, let's say, and then work our way up to positive 0.01. And finally, we'll do positive 0.001. And we'll see what values we get. So from the left-hand side, remember this is as x approaches 0 from the left-hand side. What are these values? Well, we're going to start off with negative 2, and then we're going to get negative 100, and then we're going to get negative 1000. Okay, and from the right-hand side, as x approaches 0 from the right-hand side, what are we going to get here? Well, we're going to get positive 2, we're going to get a positive 100, and we're going to get positive 1000. And what we can see here is, and again, in the middle, we can sort of think of it as the general one as x approaches 0. Okay, and what we can see here is that from the left-hand side, our limit is approaching negative 1000. And as we can see, these numbers are getting more and more and more negative. And so if we had negative 0.000000001, we would get an even more negative number. And from the right-hand side, we would get the same thing, except now we're going into the positive numbers, okay? And so our limit from the left-hand side, so our limit as x approaches 0 from the left-hand side of our function 1 over x, what is that equal to? Well, it's actually equal to negative infinity, okay? It's equal to negative infinity. And we can see that if you know the graph of 1 over x, you can see that visually, but also you can see it here from our table, and you can also see it mathematically. The smaller that this x number gets, the larger that the resulting value will be. Because remember, if you're dividing by a really small number, that small number can be written as a fraction, and that fraction is going to get flipped and multiplied. So you're going to get a really large number. And if that number is in the negatives, well, then your resulting number will be a very, very, very negative number. And if it's a positive x value, it's going to be a very, very, very positive number. Okay, so the limit as we approach x from the left-hand side is equal to negative infinity. And the limit as x approaches 0 from the right-hand side of 1 over x is actually positive infinity. Okay? And so what we can say here, in general, the limit as x approaches just 0, just in general, of 1 over x, we can say that that does not exist. You're allowed to say this. The limit itself does not exist, but the limit from the left and the limit from the right does exist. We can see it from our table. We can see it from our equation. And if we know what the graph looks like, we can see it in the graph as well. Okay? And so this kind of brings up one other rule where we can say if the limit as x approaches some number a from either the right-hand side or the left-hand side, I'm going to write that as kind of a plus minus, of some function f of x, is equal to either positive or negative infinity, okay, then we have a vertical asymptote. Vertical asymptote. Asymptote. Okay, so if we ever find ourselves getting a positive infinity or a negative infinity, we know that we're going to have a vertical asymptote at where we're going to have this vertical asymptote. We're going to have it at x equals a. Okay, so we're going to have it whatever this a number is. So in this case, we can say that we are going to have a vertical asymptote at 0. Okay. And of course, this is kind of an extension of the first rule that we talked about. Since this limit is plus minus infinity, that also means that the limit itself in general doesn't exist. But that's kind of just an extension of the first rule, so I won't rewrite it. Okay, so that is we found two limits here using tables, and we also discussed some really interesting things. First one being this idea of limits from the left hand side and from the right hand side, and that they need to exist on both sides and they need to be the same value in order for the limit in general to exist. And then we showed that it's actually possible for those values to not be the same, in this case where we had -1 and +1. And then we also found out that limits can also go to positive and negative infinity. And in that scenario, here we figured out that that means that we have a vertical asymptote at wherever that limit is. Okay, so that's everything for this video. In the next video on limits, we're going to be talking about some properties of limits, some rules, and we're actually going to use those properties and rules to properly find a limit without having to use a table and type in numbers in our calculator. Okay, so that's coming up in the next video.